Here is an overview for our project. We named our project Grid Guys because of the inclusion of the main element in the playing field, an 8x11 grid. In this grid, there is an array of 4x4 red and green cylinders. So these cylinders are spread out so that between each row and column, there is an empty line, and we use these empty lines for our rovers to navigate the grid. Now at the top of the grid, we have two dispensers, one for red and one for green cylinders, where the rovers can come to pick up new cylinders. And then between the dispensers, we have a dump point where our builder will take completed cylinders to be dumped off. Also near the top, we have the rover start points. So now we'll take a look at the two rovers. The first rover is Mad Max the scanner. And as you can see, Mad Max is quite a feisty one. He likes to run on his own agenda. The scanner's job is to traverse the grid and scan each block to determine its color and then send that data to the server. Then the builder can begin its task. The builder's task is to remove incorrect cylinders from the grid and replace them with the correct color in that same position. And then this data will be sent to the server where the user can see the current state of the grid.
Here we see Mad Max, the scanner rover in his natural habitat. Max begins his day lurking in his spawn location at grid coordinates 1-9. He glares disdainfully at the playfield in the distance, set with an assortment of red and green blocks. Max asks his boss, the server, "What is my purpose in life?" The server responds, "You're a scanner, Max." Max then asks the server, "Should I go to work yet?" "How about now?" The server says, "Get to it, Max." So Max departs, following the beat of his timer interrupt. He has to make the long journey to grid position 1-1. He follows the path in straight lines. He wasn't exactly blessed with a face rotor. As he reaches his destination, he pauses long enough to take a reading from his front-mounted RGB sensor. He immediately begins telling the server what a horrible block he has seen. He shifts into reverse, then navigates to the next block, making sure to continually pester the server about the most recent block. His journey would continue until all blocks were scanned. Max could then return home after a hard day's work and shift into his off state for the night. Here we see Happy Harry, the builder rover. Like Max, Harry begins his morning in his spawn location. He asks the server, "What is my job?" The server responds, "You're a builder." Harry, being a good builder, requests the survey data from the server prior to taking action. The server, having already had Max do all of the work for him, or possibly just making up the server data as some sort of cruel joke, tells Harry the layout of the grid one block at a time. Harry often misses a few crucial pieces of information, so the server continually tells Harry until he's slowly driven to the point of madness and tells the server, "I have already placed a block." This is a lie. The block doesn't exist, but it works. The server tells Harry that he can go to work. Harry realizes that he doesn't have anything to build yet, so he remains at home and asks the server what he should do until the server gets an order from its boss saying, "Set the block at 1-1 to red." Harry then speeds off to the block.
So this is Sky, and I was in charge of the motor control for this project. For the motors, we use pulse width modulation to control the speed. And by using this, we actually control the duty cycle of the frequency, and then this controls the speed at which the motors operate. So on our grid, this is a pretty important deal because when we want to turn, we need to adjust the speed of one side of the treads differently than the other side of the treads. And by doing this, we can either make a wide or a very short turn. And we also use this speed control to follow lines between intersections. So if we veer off to the side on the line, we can adjust the motors to correct its position back onto the line. Originally, we placed the line following sensor on the rear of the rover, but we quickly found that this would not work out for our setup, and we moved it to the front. And after that, we were able to control the turning and line following much better for for the rovers. We found that the motor feedback was not necessary for this project. The line following sensor was enough to accomplish all of our goals. The motor task takes a command from the navigation queue, and it will update the motor speed and direction based on that command.
Hello, this is Min, and I was in charge of the sensors. The line sensor used for both rovers was the SparkFun line follower array, which consists of 8 adjacent IR sensors. The I2C protocol is used to interface with the sensor and obtain raw 8-bit unsigned integers, with each bit representing if the corresponding IR sensor is sensing a line. The RGB sensor used on the scanner rover is the TCS34725 breakout board from Adafruit. The I2C protocol is also used to interface with this sensor and obtain 3 16-bit unsigned integers representing the raw red, green, and blue values of what it's sensing in front of it. Interrupt-driven I2C communication between the PIC32 and the sensors was implemented using the peripheral library, or plib, included with MPLab in Harmony. A sensor's task served as the interface to obtain the data from both sensors about every 100 milliseconds, using the I2C implementation to read from the sensor's registers. This data would be forwarded to the navigation task via a queue.
Hey guys, Thomas here. I was in charge of making sure that Happy Harry's Claw operated correctly for the project. It was really fairly straightforward. It ran on pulse width modulation similar to the motors. The biggest difficulty was really just calibration. See, servos run with a standard duty cycle of between 1 millisecond and 2 milliseconds, with 1 millisecond being one extreme and 2 milliseconds being the other extreme. But that's for the ideal servo, and servos are never the ideal servo. So you have to do a great deal of trial and error to figure out where those extremes actually are, and then come up with a point in the middle for when you're actually grabbing. But once you have those numbers nailed down, actually implementing them is an easy task.
Hello everybody, Brian Stoneham here. My part of the project was the navigation algorithm. The navigation algorithm maintains all state information for the scanner or builder to complete their role, such as the current task that the scanner or builder is completing, the current grid position, or their orientation. It also handles communication with the server, such as on-sequence, off-sequence, initialization, and block updates. It processes data from the line sensor, the RGB sensor, and also tells the grabber when to close and open. It keeps an internal grid of information of where everything's at, such as the hard-coded spawn dispenser, block, and dump position, but the color of these blocks are not hard-coded. It first computes a linear target hop or a grid position to move to on the way to the final position. It then computes the direction it needs to face, and then computes which direction to turn to if needed. It then executes motor commands to complete a turn if necessary, then move forward or reverse, and also adjusts to a line if it's currently following one.
Hey guys, it's me again. To get our project to work, we identified that the rovers would have to conform to a number of constraints. First of all, at a low level, they'd have to be able to follow the line, and then at a higher level, they'd have to be able to use the line to navigate to specific locations on the grid. They'd have to be able to come close to the blocks, they'd have to be able to identify the colors of the blocks, and they'd have to be able to grab the blocks. With experimentation, we were able to identify the distance necessary for the RGB sensor to operate as being about 1.5 centimeters, which was disappointing because this was a lot closer than we'd really hoped to have to get. We met some of these constraints and we did not meet others. We were able to get it to follow the line fairly consistently, but we really struggled to get it to navigate to specific locations right up until the end. It was also difficult to get it to consistently drive up to within 1.5 centimeters of the blocks and then stop. And further, even within that 1.5 centimeters, the RGB sensor was not always accurate in what it was detecting.
So unfortunately, our final design was not very robust, since the line sensor and navigation were easily thrown off, and the rover was not likely to recover if it messed up. Navigation relies on where the rover has started or has gone, and we didn't implement any other way to detect where it currently is on the grid. The line sensor and navigation were thrown off, often by missed or false detection of intersections and detection of how much the rover has turned. As a result, our playing field needed to be as flat as possible. In the end, integrating our individual components went smoothly as we simply needed to connect the cues that each of them used to communicate with the navigation task. Because we ran into issues getting the navigation task to work reliably, we ended up demonstrating each rover attempting to interact with one block on the grid.